Yeah, since we haven't done much leadership thing.
Oh, yeah, well, I mean, you've been organizing stuff, organizing meetings and.
Right now. Papers. Chicken. So,
Yeah, well, it's kind of good, you can update it based on, and then as the year goes on.
yeah, also for the plane ticket.
Yeah.
You probably don't buy, they have a travel agent.
Okay,
The registration.
September 15th, so next week. I need to get on
This Sunday.
this Sunday, okay. Okay,
Yeah.
I need to figure that out. Yeah, so Dr. No gave, yeah, so there is faculty travel support. I think I need to contact someone about it. Yeah, I'll figure it out.
Go through the travel agent with them. About my round trip.
Okay, that sounds.
Instead of like trying to buy it.
Yeah.
Right.
It's for part B. Yeah.
So I'm just like.
Yeah, that's probably. Okay, yeah, how do I contact the travel?
Once you start registering,
Yeah.
you can just put like travel.
Yeah.
And then for travel.
Gotcha.
Okay, you want to acquire your own. And then it just says, okay, you're done.
Okay.
I put travel agent and then they got back.
Okay, oh, nice, okay, that's useful, because I probably to get it done by Sunday.
Yeah, so it's up to you.
Okay,
Just wanted to let you know.
Gotcha.
Because I know it was in the minutes, but this is just the reminder.
yes.
I reminded
appreciate
Justin
that.
and Sam.
Yes, you reminded both Justin.
Yes. You wanna look at the plan?
Hey, what's up? Okay.
I want to go. You're gonna have that, you're supposed to say too high or too.
Okay.
I know that. Double like the average. That's probably why. I'll go somewhere. You saw Bryce down there? Bill, you don't wanna. No, I wanna be there.
Send me an email there.
This Sunday.
Yeah, 31.
I remind you. Yeah, so I wanted to.
Yeah, I'll do that. Bill?
You want to see?
Crazy.
It's ending. Hold on. You know what's right?
Yeah.
I wonder why. Put that away, man. I'm a weapon right there. It's a weapon right there. Yeah, you're gonna crash. No, I won't. It's not a mic. Pick up some down.
That part of the way. Sometimes it's like that. It's happening.
Thank you.
Yeah.
And then there's a good question.
Sure.
What?
Okay. Yeah. That's fine. Oh, no, yeah, for the conceptual question, just might do that.
Right.
Yeah, we'll probably start going with that probably next week. Yeah. Yeah, the maximum would.
Anyone on board with a chess with me? I can see.
Oh, tell me.
All the friends and then like 40 something.
I can listen to
That's higher than the.
Yeah.
Yeah, I guess that.
Ask me a question. What about the events? I'm like, there's no event there. If it's like, oh, but you had an event yesterday, I'm like, didn't get paid.
I tell you how many.
I was like, I'll pay to 5. She's like, I was rushing it, like, he was like, that makes sense, I'm rushing, this is gonna the garage. They told me it was one of these here. And I was like, what?
You know, even the yes.
Where'd you live? Yeah. It's like. Yeah. I didn't even. Hold on.
Last one, are the values on the activity one fine, or do we look at the whole selection?
Wait a second.
You know how the values for some of the dimensions.
It's like on the handout for activity one.
Yeah.
Like all the numbers in there, are those accurate to what we want to do with the activity, or should we use the numbers that we kind of go over?
Do the one that's in the PDF.
I got him in his down there, thank you.
Wait, they left.
It's like you're not. It's not gonna miss. Oh, we have a specific formula area. Well, because obviously being, I like my corner. It's a corner, right? I guess like. Oh, wait, but Brand, you know. It's Liz already. Let's go. But we can stay on this side. No, he's also gonna go.
Take the.
It's a little bit crowded. No, just right here. There's a whole row. It's wide open right here. That's crazy. I don't get this. You don't have to. Just now I missed you. This makes the.
Wow, he's emotionally mature. Love it.
Yeah, just supposed to have this seat right. Oh, yeah.
Oh,
Every single class I have with you guys, I'm like always like 2 rows away. I don't know why. It just happens.
Come with us.
And he was my friend for like 6 years.
Oh, yes.
Are we using answers today?
No.
Because
Just the lecture today. Yeah, we'll probably do answers next on Tuesday, next Tuesday.
Answers is up again.
Yes, it's up again.
where do we find the recordings?
It's on the Canvas link. You go to the weekly pages. It's.
Yeah, just so in case I need help for the activity.
Yeah.
Let's go.
It's just obvious.
Whatever. Make a move.
There's like one person that's not a team player.
Yeah.
You see, I'm getting like the other perspective. You know what? This is why we're taking off our aero packages. This is why my relativity is not happening.
That's what Mayor said to like, oh, we either have a no aero package at all for the sake of the car.
You know what? I'm going into powertrain.
I don't think they need it, no.
All right, it's 5:30. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Awesome.
Probably the last day of hot weather.
I hope so. It's supposed to cool down tomorrow, so I hope that's true. Yeah, because I'm tired of hot weather. In the class before this, I was, first of all, for those of you who came to the event yesterday, thank you for that. I appreciate your guys' company. I drank way too much soda at the event yesterday, so I was really hyped up. I couldn't go to sleep. So today I was kind of sleepwalking through the day. So I did the really smart thing at lunch, and I drank another soda to try to wake me up.
Awesome.
So it got me through the early afternoon, but then I was crashing / kind of overheating up here. So I was kind of dying last lecture, but it's cooled down, so I feel a bit better today. So
I think you should take another soda, probably.
another soda. No, I need to sleep good tonight. I can't take another soda.
Like a Red Bull?
No, Red Bull's that's gonna ruin my day. I can't take a Red Bull. But I'm feeling better, so today should be good. Okay, so today we actually got, it's not answers today, so I know that's kind of disappointing in a way, but this will be a fun lecture. And so today we're going to talk about meshing, right? So meshing, I think, is something that's unique to FEA. So if you've never done FEA or any kind of computational work, this is probably your first time that we're going to talk about meshing. Meshing is really cool. It can also be very frustrating. It's probably one of the most frustrating things that you'll do once you start to get to the projects. But today we're going to introduce it. So we're going to define what meshing is, talk about just kind of on a basic level what a good mesh is. How do we determine a good mesh, and a lot of the trade-offs that you kind of have to think about when you're determining a mesh. Okay. This is not the only time we're going to talk about meshing. So today is just kind of an introduction to just the concept. Just enough for you to kind of understand kind of the first few activities. And we're definitely going to revisit meshing later in the semester. So we talk about kind of more advanced kind of meshing concepts. But today's kind of just the first introduction, talk about the concepts and all that stuff. Okay. All right, so just a reminder. So activity 1, we did that last Thursday. That was our first time doing ANSYS. So the due date for activity 1 is this Saturday, September 14th. Just so that the due date wouldn't fall on Friday the 13th. So make sure you get that in. Originally, our second ANSYS activity was I planned it for this Thursday, but I don't want to have multiple activities kind of out there in the wild. So let's finish up. I'm going to let you guys finish up activity 1. Then when we come back on Tuesday, that's when we're going to do activity 2. Yes.
Where's the ANSYS download for like CSO softwares?
Oh, it's not through CSUF, so you download it directly from ANSYS. So if you just Google search ANSYS student, then you would download it directly from. Yeah. Yeah. Any other questions before we get started for today? Okay. All right. Let's go and get started. And so the topic for today's lecture is meshing basics. Okay. So, we've defined meshing before. So we talked about meshing on the very first day of class. So just to kind of jog your memory. So when we talk about the mesh, or we talk about kind of putting a mesh on your geometry, meshing is the process. Meshing is the process of taking a complicated geometry. So oftentimes your geometry is determined by some CAD model that you made in SolidWorks. And so when we mesh an object, we take a geometry and we break it up into lots of smaller, simpler geometries. And oftentimes, when we produce a mesh, all those smaller, simpler geometries have the exact same shape, right? So they're either all going to be triangles or tetrahedrons, or they're going to be rectangles or hexahedrons. Okay. So this has a little bit more context, just because this lecture is coming, quite a bit after the first activity. So you guys have already kind of have some context on this because we did it last Thursday. But I like to think of meshing is the way I kind of visualize it is if you think of your geometry and you think about what would it look like if I were to make a Lego version of this, then that's basically kind of the process. So you're taking your geometry, you're saying how can I recreate this geometry with a bunch of little squares or a bunch of little rectangles, and this is what it would look like. Okay. So this is necessary, or this is a necessary step for FEA, because otherwise, it would be impossible to solve our governing equations, right? So a big part of FEA is to, FEA kind of gives us the ability to solve these complicated differential equations, and we can only really do that if we have a mesh on our geometry. So, of course, in this class, we're not going to get into this, specifics of how that's done. But basically, the idea is that if you kind of already know ahead of time the shape of where you want to solve the geometry, so if you know you're solving it on a triangle, it becomes a lot easier to solve the differential equations on that shape. So if you know ahead of time that you're working with just triangles, and so you're going to solve it on 3 sides with 3 points, it becomes a lot easier to solve the equation. And even though you may have hundreds or thousands of these triangles, if you can solve it for one triangle, then you can solve it for all the triangles all together. Okay. So that's basically kind of how FE kind of works in a nutshell, right? So you break up your geometry into these simple shapes and you solve these equations on those simple shapes. Okay. And so it sounds kind of easy in theory, right? So you take your geometry, you just break it up, right? But there are literally an infinite number of ways that you can mesh your geometry. And so you're going to have to ask yourself, what size of elements do I want to use? How big of the elements do I want to use? What shape of elements do I want to use? There's other properties like the order of the elements. So we're going to talk about that today as well. Okay. And of course, just like anything, all of these decisions, what you choose for the size, what you choose for the shape, what you choose for the order, all of these will affect the quality of your simulation or the quality of your results. And so in other words, one sentence or one statement to kind of sum this up is that, there's lots of different ways to mesh a geometry, but there are better meshes than others. I don't think there's no such thing as a perfect mesh, and so there's no best mesh, but there are definitely better meshes than others. Okay. And so of course that kind of begs the question. So how do we determine if a mesh is better than the others? And so that's kind of what we're going to talk about today. Okay. And so, like I mentioned at the beginning, meshing is a very, very rich topic. There's, we could probably spend weeks talking about the different meshing, right? So we can talk about different meshing algorithms. We can talk about what's used in ANSYS. And so we can talk about different orders, different shapes, and it goes deep. And if you want to really get into the theory of meshing, there's a lot of content out there. But again, this class is the way I've kind of designed this class is kind of just for I want to present the knowledge in a way that's kind of practically useful for you guys. And so kind of with the understanding that for the most part, a lot of you are going to leave this class, you're going to use ANSYS just from the perspective of the user. And so I want to give you the information that you need to know as a user to kind of choose the best mesh or choose the best meshing parameters, and then go from there without getting too much into the weeds. Okay. All right. Any questions on this so far? Okay. So let's start with probably the most important meshing parameter, or excuse me. So let's go into this idea of better meshes then. So let's talk about what makes a good mesh. I'll jump ahead and
Professor?
Yeah.
This is a question when it comes to meshes, like on ANSYS, I guess it's a question for later on. Are we able to change like the shapes?
Oh yeah. Yeah, you have a lot of freedom in how you can choose the meshes and handles. So for activity one, the only thing I had you pick was just the size of the mesh. But there are ways to change the order, the shape. You can add kind of boundary layer regions or refinements, and so there's and there's even more stuff in it. So yeah, ANSYS has a very, very robust mesh. Probably one of the best things about the stuff.
Thank you.
Okay, so let's talk about what makes a good mesh. Okay. And so just to kind of state it very simply, a good mesh is one that will produce an accurate finite element simulation. So accuracy is an important characteristic. Okay. It is possible to kind of produce your mesh in a certain way to give you inaccurate results, and so of course you want to avoid that. And so a good mesh, first of all, will give you accurate results, but it will do so for the least amount of computational cost. And so the other consideration that we have to take into account for a mesh is the cost. Okay, so let's talk about both of these factors, and we'll talk about how they kind of relate to each other in terms of the mesh. Okay, so let's start with accuracy. So when I talk about accuracy, what I mean is your simulation's ability to accurately predict what would happen in reality if you were to kind of reproduce the same results. So in essence, whenever you're doing a finite element simulation, ultimately what you're doing is you're making a prediction of what would happen in reality. I think it's, when you're using FEA, it's very easy to kind of get, lulled a little bit into thinking that, whatever the computer produces, whatever ANSYS produces is accurate. But that can be very far from the truth. Okay? Because depending on how you set up your simulation and most importantly, how you set up your mesh, you could end up with simulation results that are, very far from reality. Okay. So it's very important to think about kind of the accuracy of your simulation. Because if you produce a simulation that's not accurate, that's not really useful to you in an engineering context. Because you want to use these simulations for design and analysis. Okay, so you want to make sure that the mesh that you choose is producing an accurate simulation. Okay? So how do you know if you're producing an accurate simulation? Generally speaking, the smaller your elements, the more accurate your simulation is going to be. So the smaller your elements, the more accurate your simulation is going to be in general. Okay? Of course, there's kind of special cases. There's special cases where if you reduce the element size, the error can actually increase, and so those are times when you have some sharp elements. But generally speaking, the smaller your elements, the more accurate your simulations. Okay, so to kind of visualize this, basically what FEA is doing is that it's approximating the solution to your equations across your element. And so the kind of the logic here is that the smaller your elements, the less approximation that it has to do. All right, so let me kind of illustrate this with kind of a visual example. Okay. So let's say, and I'm going to use kind of a one-dimensional example here. So let me go ahead and draw a Cartesian plot here. So you have X and Y. Okay. So let's say that we want to solve for a finite element approximation to the following function. So our function is kind of this parabolic looking function. So in black right here, what I have is the true solution. So using finite elements, we can try to approximate this. And the accuracy of our approximation is going to depend on the size of the elements. Okay? So let's say that we just have one very large element. So we have one element that spans from the left-hand side to the left.
Let's see.
So in blue right there, what I have is the one element approximation. So that's basically as large of an element that we can have. So it's an element that kind of spans our entire solution domain. Okay. So you can see in this case, it gets the endpoints correct, right? But in the middle, the error is actually quite high. So let's see how this improves when we make our elements smaller. Let's look at a 2-element approximation. So let's approximate this solution with 2 elements. The nice thing about 2 elements is that the direction of our solution can change when we go from 1 element. And so if I were to do a 2-element approximation, it probably would look something like this. So that's our 2-element approximation. So you can see that the error is going down, right? So because we're able to put that midpoint in there, that kind of, anchors our solution a bit better. Actually, if I were better at drawing, the error on the first section would probably be less. And of course, let me draw just one more just to kind of drive the point home. Let's do a 3-element approximation. Here. And so as the number of elements increase, or in other words, as the elements get smaller, we get better and better at approximating the solution. Right, so this was just kind of a simple one-dimensional case just to kind of illustrate this, but of course, this concept generalizes to 2D and 3D as well. Okay. Another way that I like to think about the mesh, maybe this way is a little bit more intuitive, is think about kind of how you understand resolution on kind of a digital image, right? And so generally speaking, a higher quality or more kind of higher fidelity digital image has more pixels, right? And so it's the same thing with meshes. Right? So the more pixels or the more elements that you have, generally means your elements are smaller. That's going to lead to higher. Okay. Any questions on this? Yes.
So for my question, regardless, is do we for the FEA, do we decided how big or how small our mesh material gonna be in order to have analysis on it, or it's just gonna be like universal and then we just work around?
Yeah, so it definitely depends on the simulation. So so the perfect mesh size is going to depend on whatever you're simulating. It also kind of depends loosely on the boundary conditions as well. So it's something that you kind of have to test kind of situation by
Play
situation.
around with it.
Yeah. So there is something that we're going to go over. I'll probably go over it in this lecture called the mesh convergence test. And so that's something that you can do to kind of prove that your mesh is All right, any other questions on this? Okay. So that's accuracy, right? So I think accuracy kind of pretty straightforward and kind of intuitively, I think as you use FEA some more, then you'll get a good sense of accuracy. Now, of course, element size is not the only factor that contributes to accuracy. Element size generally is the biggest contributor to it. So that's why I kind of make this. What you choose for the element shape and the element order will have an effect as well. And we'll talk about that kind of later on. But for now, let's kind of just focus our discussion just on element size. Okay. So the second factor that we have to consider when making our mesh is the computational cost. Okay. And so when I talk about computational cost, what I'm referring to is the amount of computing power, and so the amount of memory, the amount of processing that your computer has to do. But realistically, for you, the user, computational cost just relates to time. And so computational cost is kind of the general term that I use for the amount of resources it takes to run a finite element simulation.
Just like the use of a supercomputer to do some simulation.
Exactly. Yeah.
Quantum computer. Magic.
So kind of the not so fun stuff, the practical side of running a simulation. Okay. So while it's true that running a finite element simulation is a lot cheaper and a lot faster than running a physical test, it's still technically not free, right? So there's time, there's memory, processing power. Kind of a consideration that people are thinking of now, especially with AI, is the amount of electrical power that's needed to run a computational job. And so all of these have a cost. Okay. And so why is this important for your mesh? So generally speaking, the more elements that you have in your mesh, the more expensive or the more resources it's going to take to run your simulation. Some of you have actually already experienced this in activity one. So, and so I think part of activity one, I asked you to kind of experiment with the mesh size. And so if you made the mesh size too small, some of you probably found out that your computer ran out of RAM and it was very difficult for your computer to process it. So you're kind of sitting at your computer for 10, 15 minutes waiting for it to process. So yeah, things can get out of hand very quickly in finite elements if you're not careful. And so the more elements that you have in your mesh, the more time it takes to run, right? Not only does it take more time to produce the mesh, but even after you produce the mesh, it takes more time and processing power to actually run the simulation as well. Okay, and these are all very practical because when you're doing FEA in kind of a professional setting, how quickly you can get results done is actually pretty important. Okay. Now, I will say that for cost, for the most part in this class, you're not really going to get a full appreciation of what it means to have an expensive simulation versus a cheap simulation, because the versions of ANSYS that we use kind of places a hard cap on the amount of elements that you can use.
Which is have it more element.
So I don't know what the limit is for the 2024. I believe we're using the 2024 version. But in the past, for the student version, it was about 64,000 elements. But for the academic license, so the ones in this lab, it's a bit higher. So I believe it was around, I think 80,000 or 90,000. I don't remember the exact number. So ANSYS, so the versions of ANSYS that we're using does place a pretty heavy limitation on this. And so you're not really going to get a full appreciation of the costs. Because even if you push it right up to that limit, so let's say that you make a mesh with 64,000 elements, your simulation is probably still going to finish in a matter of maybe 2 minutes tops. Okay, but once you kind of get out of the classroom and you kind of use FEA in kind of a professional or even a research application, you'll see that cost is very important. And so it could mean the difference of your simulation finishing within 3 hours versus your simulation finishing in 3 weeks. It gets that much. And so I've seen, and this is even on the very big supercomputers, I've seen like research groups hog up 60% of a supercomputer for a simulation that takes a month to run. And everyone hates them because while they're running the simulation, no one else can get their work done. So so yeah, there's a huge variation in cost. You're not really going to see it in this class, but it does kind of expand right through. Okay, any questions on this? Okay. All right, so we have our two factors here. So we have accuracy and cost. And so if you kind of read the two again, you'll see that these two factors are kind of in direct competition for each other, right? And so on the one hand, for accuracy, we want to increase the amount of elements, and so we want to make the elements as small as possible to get the most accurate simulation. But in terms of cost, we want to have less elements, right? So we don't want to have as many elements as we need, as more than we need to. So accuracy and cost are competing factors. And so there's no perfect mesh that kind of satisfies both of these at the same time. And so your objective, if we kind of go back to kind of the very first statement that I led this section with. Right. And so a good mesh, a good mesh that will, for your simulation is one that will produce adequately accurate results with as little computational cost as possible. Okay? So you want to kind of find that number of elements that kind of exist in that Goldilocks zone, which gives you enough accuracy, but is not overly expensive. And so in other words, you need to design your mesh so that it's a good balance between these two. And so like I mentioned, one way that you can do this is you can run something called a mesh convergence test. You can run a mesh convergence test to kind of test, how accurate your mesh is or how reliable your results are. And in fact, if you're going to do any kind of professional work with finite elements or you're going to do any kind of research work, a mesh convergence test is basically a requirement. And so, we'll go over the details of what a mesh convergence test is later. But, everything that we kind of talked about just now with accuracy and cost, these are all kind of qualitative kind of descriptions, more elements, more accuracy, more elements, more cost. And so if you want kind of a quantitative kind of, hard line test to see, how good your mesh is, you need to run a mesh convergence test. So we'll go over that. We'll go over that kind of later. Okay, but before we kind of get to that, I want to get to the other factors of the mesh that I mentioned, element shape and element order. Before we get to that, are there any questions on just cost versus accuracy? Okay, good. Okay, so let's talk about element shapes. Okay. So remember that, when you create a finite element mesh, you're breaking down your geometry into a bunch of simpler shapes. Okay. And so those shapes is something that you can choose. Okay. And the shape that you choose does have an impact. All right. So I say that you can choose the shape, but you actually don't have that many options. So you can basically either pick a triangle or a rectangle. And the exact names of the elements depend on whether you're in 2D or 3D. So let me kind of draw it out in a table for you. We have the 2D elements and the 3D elements. And then between 2D and 3D, we have the triangular type shapes and the rectangular. Okay. So the triangular shapes in 2D is a triangle. So it looks just like that. In its most basic form, it just has 3 nodes, and so it just has all of the vertices of the triangle. The 2D rectangular shape looks like a rectangle. And it's called a quadrilateral.
Wow, true.
So in 3D, we also have a triangular shape. It's basically a 4-sided pyramid. If you play Dungeons and Dragons, it's basically your D4. Okay. And so the name that we give the triangular 3D shape is a tetrahedron. It's basically just a pyramid where all the sides are triangles. And then we have our 3-dimensional rectangular shape. And so the 3-dimensional rectangular shape goes by a lot of names. And so I often call it a box because it looks like a box. Other people call it a brick because it looks like a brick. But the official name for it is a hexahedron.
6 face.
So it gets its name because it has six faces, basically.
So the triangle got because of 5 face?
Tetra is 4.
Of
4 faces.
And then polynomial is 4.
All right, so as we kind of go through the activities, we'll start to incorporate element shape into the activities. And so you'll start to see these terms tetrahedron, mostly tetrahedron and hexahedron, because we're mostly going to be working in 3D from now on. So this is kind of just what they. Okay. So what's the difference between these two shapes? So how do they change things? Accuracy does play a role in this, but the main determination that you have to make is whether or not you can actually create a mesh with these shapes. So let's talk about the benefits of a triangular mesh first. Okay, so using triangular elements, kind of the main benefit that you get is that your meshing stage will be very stable. And so what I mean by that is that it's very, very rare for you to have any troubles creating your mesh with triangular elements. And so you can have a very complicated CAD model with lots of curvatures, lots of fine features. If you mesh it with triangular elements, so let's say you choose tetrahedrons, most likely 99% of the time you'll be able to create a mesh. That may not seem like a very good property, because you guys have only used ANSYS once and that mesh kind of produced without fail. But I will guarantee that when we get to the end of the semester and you guys are running ANSYS simulation on your own projects, on your own geometries, getting the mesh failure or the error that says your mesh failed to produce will be the most frustrating thing that you will do in this class. And so, being able to fall back on these triangular elements and be able to produce the mesh reliably is a really, really good, it's a really, really good problem. In fact, for a lot of finite element softwares outside of ANSYS, the only option that you have is just to choose triangular meshes, because the algorithm that exists to produce triangular meshes is very well documented. It's very easy to implement, and so in a lot of finite element softwares, you just don't even have a choice. You have to choose triangular elements. ANSYS kind of spoils you in a lot of ways, and they make some very difficult things with the mesh seem very trivial. And we'll talk a bit more about that. Okay, but usually, if you're running a finite element simulation for the first time, like you have a fresh geometry, you just created in SolidWorks, and you just want to get results, a triangular mesh is usually a good place to start, because it's going to be reliable and producing. The downside, or the negative part of using a triangular mesh, is that it's not very efficient at filling space. And so what I mean by that is that if you have a certain geometry and your geometry has a certain volume, and you need to fill that volume with triangles at a certain size, then it's going to take a lot of elements to completely fill that space. And so you're going to end up with meshes that have lots of elements. And what we've already talked about is that the more elements that you have, the higher your cost is, and so that's not good. Okay, but the downside is that even though triangular elements, it takes a lot of elements to fill the space, you're not necessarily getting a boost in accuracy with that amount of elements either. So another way that you can say that is that if you use a purely triangular mesh, you're adding kind of a lot of excess elements there. So you're adding a lot of excess cost, without really kind of improving the accuracy or reliability. Okay. So if you have a situation where maybe outside this class, you have to fill a very large volume of elements. And so your meshes are getting into the orders of millions or tens of millions. You probably want to look into other options than just a purely triangular mesh, because if you need to fill a space with 10 million elements, you don't want to do that with all triangles, because you're going to be adding just a lot of cost without putting it. Okay, so that's triangular elements, and that goes for both 2D and 3D. Okay, let's talk about rectangular elements. And so in contrast, rectangular elements are much more efficient at filling space. And so for the same geometry, you know, X amount of rectangular elements compared to X amount of triangular elements is going to give you a better quality solution on average, okay? They also have better approximation qualities as well. We'll dive a bit deeper into what that means kind of later in the course, but just know that, you know, element per element, you know, rectangular elements are give you kind of more bang for your buck. So on a per element basis. So on a per element basis, what I like to think about is that rectangular elements give better value per element. And so you'll get, you know, more accuracy, more reliability compared to triangular elements. So all of that seems great, right? And so, you know, when you read that, you know, it seems like, you know, you should always use rectangular elements. Of course, there's a downside. There's always a downside. And so the downside of using rectangular elements is that, you know, they are much more prone to mesh failure. So, you know, it's they're not as reliable and creating a mesh than triangular. And so a lot of the errors that you're going to get from mesh failure, they're going to be, you know, when you're trying these rectangles. So it can struggle to produce a valid mesh, especially when your geometry is complex. All right, so generally what I tell people is that, you know, you should try to go for a rectangular mesh. You should try to make it work. You know, ANSYS actually makes it very easy to do so. It's definitely not as cumbersome as if you were trying to attempt this in another software. And so if you're using ANSYS, you know, I always say just go for it. But just be prepared for getting a lot of, yeah.
Is that why, like, even in the 2D simulation we were doing, it does mostly squares and then just a few triangles?
Exactly, yeah.
So it already makes that kind of.
Exactly, right, yeah, so that's a good point. So in the activity that we did, you know, we didn't explicitly specify the shape. And so the default is that ANSYS will always try to do rectangular elements first, just because they're better quality. And then when it can't do that, it'll revert to triangles. Which is good, that's a good. So by default, if you don't specify anything, ANSYS will try to create a rectangular mesh. But you know, it doesn't always work. And so you may have to force it to go triangle. And we'll go over how to do that on our next activity next Tuesday. Okay, any questions on this? Okay. So element shape, you know, for most other softwares is actually a pretty important choice. well, sometimes you don't have a choice. Sometimes you have to choose triangles. Actually, I didn't actually start to use rectangular elements until I started this job. And then they told me how to teach ANSYS in my first semester here. So I had to learn ANSYS very quickly. And I'm like, wow, it's very easy to produce rectangular elements here. So definitely, ANSYS definitely spoils you in that sense. All right, one other factor that you have to consider in terms of the shape is the skewness of your mesh elements. Another way to talk about the skewness is the mesh quality. Let's talk about that for a second. Okay. So when you're trying to produce a mesh on an arbitrary geometry, there are going to be situations, especially near the boundaries and especially near the finer features of your geometries, where the elements may have to kind of contort itself or kind of, take kind of a weird kind of shape in order to kind of fit within your geometry. And so, if you think back to activity one and you looked at your elements, for the most part, your elements should be pretty well behaved in activity one. I mean, our geometry for activity one was very simple. But if you looked at kind of the areas around the hole, you'll probably notice that some of the elements they either reverted to a triangular element to kind of fit that space, or in the worst cases, they may be a very contorted or very kind of distorted version. And so, you may get situations. Well, let me draw an ideal element first. So let's say that you're just producing a triangular mesh, right? So ideally, all of your elements should look something like this, where all the sides are equal length, all the internal angles are equal, right? So this is kind of what I kind of, like we can label this as kind of the ideal element. Nice and balanced, pretty much as close to an equilateral triangle as possible. By the way, when we specify, so just kind of going back a little bit, when you specify the size or the length of the element, what you're specifying is this length right here. So basically, what you're specifying is the maximum cap on the side length of the element. Okay, so ideally, you would produce elements like that. And if you go back to your activity one, or if you're still working on activity one, you should see that most elements are kind of like this, although activity one, probably all of your elements are squares. Okay. But there may be situations where your elements have to get skewed. So you might produce elements. I'm going to give you kind of an extreme example. You might have to produce elements that look something like this, right? So you have maybe two very long sides of the element and one very short size. So this is what I call a skewed. Okay. And generally speaking, if you have a skewed element, that's going to lower the quality of your solution in that particular element. Okay. because you kind of have such a distorted element where, one side is significantly shorter than the others, it's going to throw the approximation of the smoothing. So you want to avoid situations like that. So you want to kind of design your mesh and like I said, ANSYS kind of already does a very good job of kind of, trying to make your mesh, try to minimize the skewness as much as possible. Okay. But you want to kind of look out for these kinds of elements.
Is the skew elements gonna throw up the data as you want to obtain?
It's not, a few skew elements, are always unavoidable, right? Unless you're creating a simulation on a perfect square, then, if you're gonna have any kind of complexity, some skewness is unavoidable. But you want to avoid a large number of skew. Because if you start to have kind of a large percentage of skewed elements, then it'll start to kind of negatively affect the simulation. A few skew elements is not going to throw your simulation. Okay. And so because this is kind of purely a geometric quality of the elements, ANSYS can actually measure this for you. So you can ask ANSYS to assess the quality of your mesh. And the way that it does that is that it basically computes or measures the skewness of every element in your mesh. Okay. Okay. So there's actually, quite a few different metrics, and so I'll show you how to do this in the activity on Tuesday. And so there's quite a few metrics that you can actually choose to assess skewness or quality. Okay. The one that I like to use is the measure that's literally just called skewness. And so skewness is often measured on a scale of 0 to 1. And so if an element has a skewness of 0, this basically means that the element is very high quality. It's as close to equilateral as possible. Of course, the opposite of that is 1. So it's kind of a sliding scale. It's kind of a ratio. Okay. And so a skewness of 1 means that your element is very skewed, and it's a poor quality. So the way ANSYS kind of measures this for you is that it computes the skewness for every single element in your mesh, and then it presents the results to you in terms of a histogram. Okay. And so what you can basically determine is the average skewness, and so you can look at the average skewness across the entire mesh. And so if you look at the average skewness, and so if your average skewness is kind of in the order of, 0.5, 0.6 or less, then usually you're in pretty good shape. That means on average, your elements are pretty high quality. And generally, ANSYS does a pretty good job of this. And so if you're using ANSYS, this is usually not something you have to worry about unless you have a very kind of complex and strange geometry. You can also see the max skewness, which will basically tell you the element with the maximum skewness in your mesh. Now, people look at this metric and they kind of panic sometimes, because sometimes the max skewness is like 0.95, right? The max skewness I find is not the best metric because odds are if you have a geometry with just any kind of complexity, there's probably going to be at least one element that's kind of very skewed. So I don't really pay attention to the max skewness all that much, but it can be kind of interesting to see. Right? And so oftentimes you're going to see this above 0.9. There's no need to panic in that case. Okay. But if your max skewness is something less than like 0.7 or 0.8, then your mesh is actually really, really good. Okay. But generally speaking, your max skewness, you'll probably get something above 0.9. But usually it's not anything to worry about. Okay. As long as your average skewness is kind of in that ballpark of 0.5, 0.6, or even less than that, then you're good. All right. Any questions on this?
Is this the question? With 0.5, 50% of the elements are skewed?
No, so that's a measurement per element. So when I talk about a skewness of 0.5, it's basically a ratio. So it's a ratio of kind of the max. It's basically of the minimum edge length to the maximum edge length. And then there's kind of some complicated formula.
Okay.
Yeah. So an average skewness of 0.5, that means on average, it's going to measure a skewness for every single element. On average, it's about 0.5.
So half of them.
No, so it's a measure of the shape itself. Yeah. So if you have an average skewness of 0.5, that means across all of your elements, the average skewness is about 0.
Oh,
Yeah. And you'll be able to visually see it too. So if you have a lot of very skewed elements, you'll be able to visually see it in your mesh. And so generally the solution is that if you have a lot of skewed elements, is just to reduce the size of the element. So if you reduce the size, you kind of fix that skewness problem. Reducing the element size is kind of a solution to most of the element problems that you're going to have. Unfortunately, it comes with the cost of, cost. But reducing the size fixes a lot of these issues. Any other questions on skewness? Okay. All right. So the last thing I want to go over today, we may not have time to fully cover it, but we'll finish it up on Thursday, is the element order. So this is something that we didn't touch at all in activity 1. And to be honest, for most of the class, we're not really going to touch it either. Just because, again, ANSYS kind of spoils you for this as well. But normally element order is a very important consideration for the mesh. Okay. Okay. So what do I mean by element order? So let me give you kind of the options that you have, and then we'll kind of talk about kind of what they mean. Okay. And so if you want to set the order of your elements, you can go into ANSYS and set this. You'll see that you have kind of 2 options available to you. Okay. And so your 2 options are either linear order or quadratic. Those are your 2 options. And what those are referring to is the order of a polynomial.
oh. We go back to math.
FEA is all math. I'm shielding you guys from all the math by doing it.
Yes. I love math.
And so you may be wondering, what does a polynomial have to do with ANSYS at all? And so if you recall, ANSYS, or FEA in general, what we're doing is we're approximating solutions to differential equations, right? And so the way that we do that is that, instead of solving the differential equation, what FEA will do is that it will approximate the solution with a polynomial. Just to kind of illustrate this, a linear polynomial would look something like this. And so a generic linear function has 2 degrees of freedom. So we have our constant term a0, and we have our linear term a1x. And our quadratic function has 3 degrees of freedom. So it's a0 plus a1x plus a2x squared. Okay. Okay. So, just to kind of give you a little bit of explanation on kind of the significance of this choice, what makes FEA kind of unique compared to probably most of the other mathematical techniques that you've learned in your other classes is that FEA starts by assuming a form of the solution. So even before it starts to solve, what it's saying is that, all right, I've already decided ahead of time that I'm going to find the best quadratic function or the best linear function that solves this equation. Okay. Now that's very different, right? And so if you think of, if you think back to your differential equations class, you think back to 308, you don't assume a form of the solution. You look at the equation, you find the solution, and just whatever form the solution happens to be, that's the form. Okay. FEA kind of does this backwards. So it says that, I'm going to find the best quadratic solution to this problem. Okay. So of course, what you assume that solution to be is going to have a big impact on whatever the solution ends up being, right? And so this choice of order is you're basically choosing the form of the solution within each element. So if you choose a linear order, then your solution will be linear across your element. If you choose a quadratic order, your solution is going to be quadratic. Okay. All right. So what's the trade-offs? And so what do when would you choose linear and when would you choose quadratic? Well, it all comes down to cost versus accuracy again. Okay. So a linear order generally will be cheaper to compute. It's going to take less computational resources, less memory, less processing power to do that. But on the downside is that it's generally less accurate. And then of course, quadratic order elements are the opposite of that. So quadratic elements are more expensive to compute per element, but it gives you a better quality solution per element. Okay. So one benefit that quadratic elements particularly have, because they have this kind of x squared term, is that quadratic elements are much better at approximating locations where your solution is changing rapidly. Another another benefit of quadratic elements is that if you're interested in qualities that are computed based on the derivative of the solution. So if you think back to a couple lectures ago, we talked about primary variables and derived variables. Quadratic elements are much better, much better at computing derived points. So things like stresses and strains, quadratic elements are much better. And so for that reason, the benefit for quadratic elements, heavily outweigh the cons in this case. And so, for this class, because ANSYS makes it so easy, it's literally just a drop-down menu. 99% of the time, you're going to use quadratic elements. Within ANSYS, there's really not many practical reasons that you could use linear elements. Maybe if you're doing something simple like a thermal simulation or something like that, maybe linear order might be more appropriate there. You might be forced into using linear elements if you're doing like a fluid flow simulation just for stability's case. But for structural simulations, there's really no reason to choose linear elements over quadratic. Again, this is something that kind of ANSYS kind of spoils you on. Usually it's not trivial to implement quadratic elements. And in fact, if you use a lot of other softwares won't even give you the option of quadratic elements, so just force them to linear. But because ANSYS makes it so easy, for the most part, we're almost always going to use quadratic elements. But I at least wanted to go over this just to kind of, just so that you can see the setting, you can kind of appreciate what it means, and then just pick quadratic. All right, any final questions before we wrap it up for today? Okay, all right, so that's all we got time for today. And so when we come back on Thursday, we'll start talking about boundary conditions. So thank you guys for coming today. Hopefully the weather cools down for you guys and it gets more bearable outside. But yeah, so thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you on Thursday.
Thanks a lot. A rap formula game. What we learned today. Always use quadratic. No, I don't want EV.
Like you said, just have to check.
Dr. Chad, do you like EV?
I learned
Dr. Chad, do you like EV? Do you like EV?
I don't drive one, but I.
For me, it's a battery and a mouse. What's that called?
Wow, it's a very complex battery, very complex.
Yeah, very complex battery. I think it's like 100 something pack of Samsung on it.
Yeah.
That's all right, thank you.
Yeah.
And see you tomorrow.
Yeah, see you tomorrow.
All right, well, then Bob, I'll get back to each one. Definitely have nothing to do. Nothing at all. Not a thing at all.